Thank you for joining the Once Changing the World, India's first Future Tech Meets Sustainability podcast. I'm your host, Eddie Avil, and today I'm delighted and honored to have with me Mr. Daniele Pucci, who's the Principal Researcher, Head of Artificial and Mechanical Intelligence at the Italian Institute of Technology. He has been a postdoc at IIT, working within the EU project CoDyCo, focusing on the balancing problem of the iCub humanoid robot, and he has also laid the basis for the aerial humanoid robotics. He was awarded the Innovator of the Year under 35 Europe from the MIT Technology Review magazine for conceiving the iRonCub, the first jet-powered flying humanoid robot. And Daniel was also the leader of the iCub team during the ANA Avatar XPRIZE, a 4-year, 10 million international competition for making robotics avatar. So Daniel, really appreciate you taking time and being part of the podcast. I think it'd be great if you could, give the audience an understanding about what a humanoid robot is and what's the challenges of building a humanoid robot.
Yeah, Eddie, so thank you very much for inviting me, and it's a pleasure to talk a little bit also myself. So basically, a humanoid robot is essentially composed of three things. So the first one is a mechanical structures, so that somehow resembles a human being. And so it has a certain number of joints that are similar to those of the human being, like shoulders, elbow, wrist, and usually structured into four main pieces. So we connected centrally. So you have arms, legs, and main body. Then clearly the head plays a role, but not all the time. And then the second component is clearly the intelligence of the robot, which has to process inputs and provide outputs. So the inputs are sensors, and the output is the motor commands. So then we get to the third point, which is the sensory motor architecture, which is sensors and actuators. So you have one body, which has a structure like a human being, then an intelligence, which has to process sensory motor informations, and then you have sensors and actuators, and then make the humanoid robot move. So that's essentially what a humanoid robot is. And the complexities are many. So just to mention a few. Clearly, some humanoid robots are intended for human-robot interactions and multi-purpose. There is not really a big reason why you want to do a humanoid robot if you don't want to make it do several things. Okay, because if you stick with one goal or one objective, you are not going to go with a humanoid robot because it's not going to be as efficient as a machine that does only that task. And it's been conceived only for that task. So the main at the high level, the main complexity is that you want a machine that does many things in an environment thought and built for humans, and anthropomorphic environment. So you have an environment which is somehow that we shaped for ourselves, and then we want to make basically beings, artificial beings that act like us. And so the multipurpose is trying to scale the intelligence of the robot combined with the body for multipurpose is really one of the challenging tasks that researchers have to address.
Through the years, we've seen that there are various companies such as Boston Dynamics and Hanson Robotics and many others who spent years in trying to emulate what a human does and have failed, but over the years have been becoming better and better and better at it. We see all these Boston Dynamics now doing these acrobats and stuff like that. But there have been various videos floating on the net where you with simple touch, the robot kind of falls down. It's still unable to hold a simple bottle and kind of understand its environment itself. So it comes with a multi-pronged problem of building a humanoid. Where are you currently at in solving those problems, and what are those specific areas of problems that you specifically are looking into creating a humanoid robot?
First of all, we are trying to build up on the knowledge of the iCub. iCub has been this idea of building a humanoid robot child, which could develop intelligence by interacting with the body, with the environment. So human-robot interaction and human-environment interaction was really important. Okay, so now iCub has been a platform that was basically meant for research. And what we're trying to do now is to make that research platform grow up towards specific applications. And we are trying to do so while working not only, let's say, in the autonomy of the robot per se, but so the intelligence, the so-called cognitive intelligence of the system, but also the motor intelligence of the system, which sometimes humans give for granted. I mean, just to give you an example, when we walk, when humans walk, they walk mostly at minimal energy. So we don't need much processing when we walk. Actually, engineers are able to make passive walkers, which are mechanical structures that walk without AI, without sensors, without actuators, but they walk. What does it mean? It means that a degree of intelligence can be delegated to the robot, to the body itself. So how we build up bodies might encompass and entail a level of intelligence. So one of the big things that we are trying to do here is try to understand how the intelligence of the system, so that the intelligence, like the overall intelligence, not only the cognitive intelligence, but also the motor intelligence. So how part of this intelligence can be entailed inside the body itself. Okay, and it is not easy because really it boils down to the fundamental characteristics of the body, like the densities, like the material, like how you connect the joints of the robot, and this has also an impact on the overall cognitive intelligence and physical characteristics of the system. Imagine, for instance, if you have to shake the hand of a robot. So if the hand is soft, or if the hand is really rigid and hard, you're going to have two different perceptions of this human-robot interaction. So the body itself has an incredible high number of impacts also in human-robot interaction, not only motion. So that's what we are trying to do. So we're trying to give humanoid robots a level of, let's say, cognitive intelligence, but with a perspective on the robot, on the robot body.
Daniel, I think it'd be great if you could speak about the potential applications that you envision for both your iCub humanoid robot as well as the iRonCub jet-powered flying humanoid robot.
Concerning the evolution of the iCub, we are trying to make it evolve along basically two really main directions. Okay, so the first one is human-robot interaction and human-robot collaboration. So the idea and the vision here is that the future warehouses or in the future hospitals, there will be systems, intelligent systems in the form of human robots that can help physically future workers. And this is to answer a real problem that somehow, or at least our society is living. And just to give you a couple of data, if you look at even European or also Italian data for the number of reports that workers do when they have to stop for health reasons their work, 70% of these are due to the musculoskeletal system and the so-called connective tissue, which means the classical back pains are still the main blockers for at least for Italy for sure, but also for Europe, of the production systems. Okay, and so what we would like to have there is that future robot collaborators or robot companions will have a perspective on our body. So they are trying to understand, they have to understand when we do those tasks that put at risk our physical system, and then they intervene and they collaborate us to reduce the so-called biomechanical risk. So this is a clear first direction that we have, trying to reduce the risks of future workers in future work environments. In this context, there is a caveat here, because if you want to decrease the risks of future workers, one possible approaches in certain cases is to decouple the risky environment and the worker. Just think of, I don't know, a nuclear plant or a polluted area where the worker has to get in. So you really don't want human-robot collaboration there. You want the robot to be at risk, and you want the worker to be safe. So you have to decouple these two. And that's why we are working a lot onto avatar systems, where you can wear wearable technologies, headsets, and gloves, and then you simply are teleported inside this body. And I mean, one of the projections that we have in this sub case is that when you have, for instance, injured people with physical problems that cannot, or physically impaired people, these avatar applications can give the body back to these people. Okay, so there are a certain number of pathologies with an EDSS really high, which is an indicator for the mobility. So when they cannot move, they're forced to stay at home, then you might basically give them back the body, thanks to the robotic body. So the avatars is also a societal impact in this perspective. Then the other big application that we're working on is disaster response. So disaster response, what does it mean? You have an earthquake, you have a flood, you have fire. So you would like to have systems that then go there and once again do not put at risk the life of the operator in those cases that are emergency operators. And in this specific scenario, what we're trying to do is that we're trying to have a platform which combines walking, flying, and manipulation. So these three capabilities, and that's why we conceived the iRonCub. The iRonCub is this prototype for flying human robot that can move from one place to another thanks to jet turbines. So we are evolving the iCub into two different directions. One is risk prevention at work, and the other one is disaster response. For the first one, we are developing ergoCub, which is the output of a joint venture with INAIL, which is the Italian Institute for Work Accident Prevention, and the other one is iRonCub, which is this prototype for flying humanoid robots.
When do you think these robots are going to go to the market? What are the challenges for it from moving from the research lab area to the market?
So I believe that now the humanoid robotics somehow is evolving. So it's getting closer from prototypes to real products. So I believe that really now there is a bifurcation going on. Okay. And because the technology at the motors and the sensors level is enough in order to put together a robot that can do some stuff in a warehouse for 6-7 hours, and probably it has to stop, it has to recharge a little bit, but then somehow as a real worker, 1 hour stop and then you get back to work. So we are really getting closer to this somehow evolution of humanoid robotics. So it's possible that in the next 5 years, two things basically will happen. First, that humanoid robots in 5 years will be what drones and quadrotors are now. Because probably you remember that in the early 2010, drones were only for labs. Now you go to the stores and you buy them. So it's possible that all these monies that also big companies are injecting into the human robotics world will make this transition, okay? Will make the transition for humanoid robots to be early prototypes to products. So in five years, you really have the store and you buy the humanoid robots you like the more, clearly for some specific applications. It's difficult to imagine technology or humanoid robot that does anything. Okay, technology has always somehow proceeded by specializing to be more efficient, okay, not generalizing. So this is a paradox that humanoid robots have to face. The other thing that might happen, however, is that despite all these resources that now are being injected into the humanoid robotics world, we will see that, well, technology is not ready yet to do a multi-purpose robot. And this might happen. Look at what happens with autonomous vehicles. How long have we been talking about cars that go around autonomously? That did not happen. That is wishful thinking. It did not happen. So it might also happen that somehow this is going to face that similar problem, because making a humanoid robot that is here and does many things is like addressing the problem of autonomous vehicles, but more complex because you have to deal with humans. So it's a more complex problem. Okay. So, and then we might have the winter. In that case, we might have the winter of humanoid robotics, because people will say, well, even if we have been giving all this money and all these attempts failed, so we have to wait for the technology to go forward. So this bifurcation probably in 5 years will lead to these two things. Either we get humanoid robots that will become products and you go to the store, you buy them, or there will be the winter. So concerning then what are the challenges now in order to make the transition, well, probably are basically three, the difficulties for the transition. The first one is technological. These robots, if they fall, they break. So especially the electrical ones, if they fall, they break. So we have to understand how make them repair themselves or not break in the first instance. So, but there is a technological problem there. And really, humanoid robots fall much more than what humans do. And even if it's not really clear from videos, but they do. So this is a first problem. Then the second problem is if you want a normative problem. So we have to understand how humanoid robots then can be certified. And this is not easy, because usually you do not certify the product, you certify the applications. And if you have humans in the middle that interact with robots, at the insurance level, it's going to be a mess. If the robot falls and injures someone, who pays? And so let's say the normative, all the normative infrastructure around normative and legal infrastructure and context around human robotics has to evolve in order to somehow set up for the transition from prototypes to products. And the third one is acceptability. This is something that sometimes it's not really mentioned, but we can do great technologies, but if the workers do not, for instance, do not accept them, then it's going to be useless. So just to make an example, we have been conducting polls with real workers. We involved about 1,000 real workers and say, okay, so assume that you have humanoid robots here. What is the expression of the humanoid robots to give you feedback? Or would you be fine to have the humanoid robots in a certain number of cases? And so it was really intricate, the pool. But and then we have been monitoring the facial expressions of workers, just to give you an example. Okay, in order to engineer back the feelings of the worker. So as soon as the humanoid robot was doing something that the worker actually now is doing, anger increased. So it's not really easy. Okay, so you have to understand how to somehow make this technology accept for the future work environment. So.
Right. Yeah. So I think there's multi-pronged problem besides the technological problem, the hardware and the software. There's also the acceptance problem where humans understand how to coexist with another species or sorts, because here we are on the verge of possibly building something which is silicon-based mechanical in the reflection of human being. And there are multi-pronged problems to even get it closer to what we humans can do dexterously as well as cognitively, because there's so much happening over there. You had also participated in the ANA Avatar XPRIZE competition. Could you share some highlights of the competition, some things that you have learned, and how is the robot, both your iCub and iRonCub, progressed from the Avatar XPRIZE competition till now?
The ANA Avatar XPRIZE has been a fantastic journey for us. It's been a 4-year competition, and in the beginning there were 77 teams. So it's been really through phases. So then we got to the finals in the second place. So this is what I wanted to say, because it's been a really proud for us. But then the finals were another story. So in the beginning, the competition was more in human-robot interaction and somehow embodiment. Then it changed more or less into a race. Like making things really, really fast. And here, really, you bump against the principle that we said before. So if you want speed, and you, for instance, you have a flat terrain, and you have to take one object and bring it to another place, just to give you an example, humanoid robots really suffer. Because clearly, if you have two wheels, and you put an arm on top of these two wheels, and then you run, because they speed up, humanoid robots cannot compete with the legs now. Okay, and probably never against wheels, or it's hard to imagine. Let's say that a highly optimized wheel will lose against a highly optimized human robot. Anyways, so the lesson, one of the lessons that we learned is that, well, legs are good, are cool, but still they pose a problem in a certain number of applications where the performance indices are particular, like speed. If you want to go really fast, well, you have to understand if the human robot morphology is really the one that you wanted. Then another thing that we learned is that manipulation of human robots is, at least our, is really complex. And once again, having a highly complex and dexterous hand is cool, but on the other hand, may make things really not robust, because if you increase the complexity, it's going to be more complex to somehow grasp easy objects. Okay, so complexity helps sometimes for complex stuff. Okay, so if you over-complexify the problem, then you're going to lose in terms of performance indices. And so these are basically locomotion and manipulation of humanoid robots. Basically, have to be understood better for the specific tasks that I have to deal with. So this is one of the things that we really learned. Okay, and then the other thing that we really learned is that if you want to teleoperate a robot remotely, the operator needs a certain number of interfaces. Just to make an example, if the robot had to walk, then we have to understand how to perceive the intent of the operator to walk, and then project this onto the human robot. So I've been experimenting this with different things. First, we had an omnidirectional treadmill where the human was walking in place because the feet were sliding. And then these were mapped onto the humanoid robot. But then this didn't really work really well because the human could not move sideways. It could not take steps sideways. So then we came up with other solutions, like for shoes, and then we implemented them. But then once you get into the robot, you are really decoupled from your real environment. So we suddenly learned that people might fall in the real environment because they completely lost their sense of perception because they were the robot at a certain point. Okay, so the robot was walking around, but and was not falling. But then the human operating the robot was standing, and then it was losing the sense of balance. So the operator interfaces is not an easy thing to be dealt with for teleoperation. Then concerning the biggest differences between the ergoCub and the iRonCub, concerning the previous versions of the iCub, also these are many. So just to give you a little bit of background, the iCub was a robot child. So the weight was more or less 33 kilos. The height was 1 meter. and it had many tendons in order to basically connect the motors with the joints. And this was fine because basically the tendons acted like fuses. So if you push too much the joint, then you didn't break the robot, you didn't break the motor, but you would have broken the tendon. So at the mechanical level, you had a structure which had many tendons. It was tall, more or less 1 meter, and had fragile hands. The hand really broke continuously, and it was not able really to walk fast. So the ergoCub took steps into this direction. So the ergoCub is 1.5 meter tall, so it's more or less half a meter taller than the iCub. The hands have been completely redesigned. The wrists have been redesigned. Also the weight distribution has been optimized for locomotion. So it walks more or less 3 times as fast as the iCub did. And then it has also clearly new computation units. It has a GPU in the head, a CPU in the chest, it has LiDAR, it has RGBD sensors that didn't have the iCub, but the face expressions have been simplified. If you look at the iCub, you basically see a humanoid robot child. So you have a different robot, half meter taller, more sensors, more new actuators, new hands, much faster in walking. Concerning the iRonCub, well, the iRonCub has been it's a different story because we didn't have the economic force to build another robot. So the idea was, let's take one of the iCubs and make a certain number of hardware modifications in order to equip it with jets. And then this is what we did. So basically, you have jet turbines attached to the iRonCub, and jet turbines have also the problems that they might explode because you get 800 degrees Celsius outside. You get fire, half a meter fire, sometimes supersonic speeds at the emission cones. So you have basically 2 big problems. The first one is that you get the dynamic pressure problems because the gas outputs at really somehow high speed, so it breaks anything it finds. And then high temperature, it melts anything that it finds. So we had to redesign the lower body of the iCub with a special aerogel and fiberglass because we wanted to deal with these 2 problems. So dynamic pressure and then also temperature. So it's a different beast, the iRonCub. So actually it's there. So basically you get these jets attached to the robot. You get this the covers of the robot of the lower body have been redesigned, and also the power units have been somehow augmented because then you have to do really fast computations in order to react during flight. So this is basically the main differences between the iCub, the old iCub, and ergoCub and iRonCub.
Thank you for explaining it, Daniel, for all the robots that you worked on. Now, you mentioned that most of these robots currently are still basically teleoperated in some ways, where they are at the back end being controlled by a human. How do you see that going forward? Because I mean, it's not completely teleoperated. There are the robots which kind of understands the environment and is able to walk and things like that. What's the capabilities when it comes to iRonCub and iCub? What all does it do? I mean, can it is it automated? Is it still teleoperated? Maybe will be great if you could talk about that.
Yeah, so basically concerning the teleoperation, so one of the big opportunities that teleoperation is giving us, at least, is to advance autonomy. We were amazed, I have to say, to see how fast we could move from complete teleoperation, but complete teleoperation, to complete autonomy for few tasks that we never could imagine. Okay, so and you do this by it doesn't happen by chance. So you have to really get quality data. And the avatar infrastructure that we have been building for years somehow thinks all data coming from sensors, images, IMUs, encoders, force sensors, current sensors, but you have to get them synced. Okay, it's important that you have these data acquisition systems that really sync and provide high quality data. Once you get this high quality data, then you have the hope to make steps towards autonomy. And this is what is happening right now. One of the possibilities that we do behavior extraction from videos, because we have YouTube. YouTube is full of videos. Why can't we then reverse engineer the physics and then get positions, but then also forces? So the dynamics of objects is not really easy. So we have big competences here in the so-called inverse dynamics problems or force estimation. So this is the direction that we would like to explore. Okay, then to make steps into of the autonomy by using videos. But then videos, then you have to get back to dynamics and forces and torques. So this is not going to be easy. And concerning the actual capabilities now, well, the ergoCub is a prototype that is really conceived to somehow collaborate with you. So bring boxes around. So yeah, and simple manipulation tasks. So big boxes or like little objects. And that's basically its main now capabilities. We can do that effectively when it is teleoperated or push buttons. Okay. Clearly now we have also proof of concept for it when it is autonomous. Okay, there is still not the feature parity because there is something that we're working on. But let's say we are really proceeding. I have to say we're taking important steps recently in this direction.
The best AI researchers are working towards building general purpose intelligent, and there are robotic companies who are working towards building general purpose robots. There's Figure, there's Tesla with Optimus, there's Engineered Arts with Ameca, there's Sanctuary, and there's so many others who are trying to build humanoids which has general purpose robots. There was this recent talk which I saw of Jim Fan, from NVIDIA, who spoke about foundational models for building generalized robots. And he said that to build a general purpose robot, you need to build an agent model that generalizes across virtual worlds and real worlds. What are your thoughts on the way to achieving a general purpose robot?
Well, if you want to have something that does many things, and because general purpose, I don't know exactly somehow. I know that it's a really nice word, but what does it mean? Okay, that does anything that human does? Well, it's difficult, right? So it's going to be difficult. But let's say, I like to say, let's start with three. Let's start with three tasks. Okay, and then we want to scale these three to 30, 100. Okay, so that we have also performance indices. Okay, of general purpose. So how can we do that? Well, this is something really, really. This is a nice question. My feeling is that we have to work a lot on perception and inject clearly perception, but also tactile sensors, for instance, that are a little bit disregarded. Okay, right now. Inside these machine learning models. Okay, and then basically you have to really take steps towards multimodal. So you would like to have tactile sensors, vision sensors, and then you would like to have audio clearly inside the machine learning. Because if you look at the numbers, basically text is really low bandwidth. Okay, people cannot read many words per minute. So if you translate that into the number of tokens, just to make a concrete example, there was also Jan LeCun talking about this. You would say that somehow the data that people would need to read in order to train these models, like it's years. But then if you take into account vision instead, well, vision it's higher bandwidth. But then if you complement vision with sensory motor sensors like tactile or also attitudes of your body. Okay, the information really are many, and then you have to basically understand how to collect this information first. So you get the hardware problem, and then you have also the problem of somehow generating this data, because this is not easy. We were talking about it, like teleoperation can be a way to generate data, but then, well, it's not easy, right? Because then you have to have many tasks going on and many hours of teleoperation. So having digital models that generate this data may really be helpful. So clearly, NVIDIA is pushing a lot on this simulator, and we completely share this vision. There is a problem there, which is the sim-to-real gap. So the distance between the real data and the simulated data is still high. So if you get a human robot walking into the simulated environment and you go there, you click play onto the robot, the real robot, it's not going to work 98% of the times. Okay. So there is a big problem of the sim to real gap. And in this context, really, machine learning can do a lot, because then you have to understand how to bridge this gap, and then develop models that can make simulators better. And then you can have better data, multimodal data, and in large quantities train these models. So quality data for multimodal robots is really one of the things that we have to work on.
Right. Yeah. So there's quite a lot of problem that still needs to be solved to kind of move on to whatever we think of what a general purpose robot is or will be. Daniel, really appreciate you taking time and being part of the podcast. You mentioned that possibly maybe in 5 years, you would have these robots going from lab to the market. Paint a picture of what the world is going to look like in the next 10 years. And you've been invested in the field of robotics as well as AI, and both you need the hardware as well as AI to kind of, come together to build possibly these humanoid robots which have the same dexterous capabilities as us. Then maybe possibly we could think about the cognitive capabilities, because that again is something which is going to come later. And then possibly the last in line would be like maybe robots that are possibly sentient. Maybe they're conscious. What's your idea of that robot that we're talking about? Maybe that we have shown in these movies, which are like conscious robots, which possibly will be able to coexist with us beautifully. First, is it even possible to possibly emulate us, or not at all? It would be great if you could leave your thoughts on that.
Well, I mean, trying to emulate, let's say, humans is not only let's say, mechanical problem, right? I mean, there is a lot of that we have to learn about the brain, and there is but a lot we have to learn about the brain and somehow how we develop the cognitive processes. What I somehow think is that right now, more or less, it happened something similar to what happened in 1903. What happened in 1903? In 1903, it happened that basically people didn't have really a clear understanding on how aerodynamics worked and why birds fly. And at a certain time, a bunch of guys started to do tests with these prototypes, and then they started to fly. Okay, so and then the airplane started to fly. Okay, wow! So that really proved that things were possible. So for one part of the artificial intelligence world, that basically, in my somehow perspective, what happened. So we made the aircraft fly, and we don't know really why, because the theory behind machine learning is understood, but up to a certain level. So we don't know how to achieve a certain level of, for instance, scalability in terms of human capabilities and etc. But clearly, the recent advancements really show that we can take these sort of black box approaches where if you get enough data, then the capabilities that you want really emerge. Okay, so for robots, then it's also a matter of data, acquiring data, because we'll be injecting information through the keyboard. What is the equivalent then for robots? No, well, how can we inject enough data? Well, it's not easy. Vision for sure. Okay, we have to have a lot of videos of humans moving in order then to acquire data, but probably it's not enough. It's not enough because from vision you cannot have everything. Okay, then you have to build models of tactile sensors, force sensors, and then tendons, or all the dynamics. It's not really easy to be reverse engineered. So probably we need other sources of data in order to get then enough quality data that then can be used in these big models that then also make this behavior composition machine for generating then a robot that does many, many things. Okay, so this is one of the challenges. So it's difficult to see how the world will be in 10 years in terms of humanoid robotics. If I look back, I arrived here 10 years ago at IIT. We had Atlas doing already many things. Then we evolved, but not incredibly, okay, from the body point of view, from the characteristics and capabilities of the doing things, okay, so from robotics. But I guess that the bifurcation we were talking before might happen in the next 10 years. Let's say in 10 years, either we will be talking about, well, it's still really difficult to make a multi-purpose humanoid robots, or we might have the chance to buy some of the humanoid robots in some stores. So these are the two things that might happen.
Right. Daniel, really, really appreciate you taking time, being part of the podcast. Wish you the very best. And I hope that the iCub humanoid robot and the iRonCub robot moves from lab to the markets and creates applications and merges with the humans in a beautiful way where they kind of coexist. So wish you the very best. And to my listeners, if you like what you see in here, then please press the subscribe button. Until next time, see you guys. Bye-bye. Thank you. Really appreciate this.
Thank you. Bye all.